Hello to anyone who's watching this video. This is the first video in the series where I go through this book. It's called 50 Challenging Problems of Probability. It's by Frederick Mosteller, who's a professor at Harvard University. It's a pretty popular book, and I think it's a very good book if you are interested in probability problems or you want to get better at them. I'll be going through every one of these problems in different videos and recording what I learned while trying to solve these problems and how I solved them. The reason I'm recording this is so I can look back at how my problem solving will improve as I gain experience in solving problems. Question number 1 is called the sock drawer problem. A drawer contains red socks and black socks. When 2 socks are drawn at random, the probability that both of them are red is 1/2. Part A says, how small can the number of socks in the drawer be? And part B says, how small if the number of black socks is even? Automatically reading this problem, you can tell that part A is going to be a little simpler than part B. For part A, you can kind of just do a little bit of plug and play. So we know that we're drawing 2 socks at random, and the drawer contains red socks and black socks. So I'm going to use R to denote the red socks and B to denote the black socks. We're also told that the probability when we pick 2 socks at random that both are red is 1/2. We know that on our first draw, our probability of getting a red sock is the number of red socks over the total socks. And on our second one, since there is 1 less red sock and 1 less total sock in the drawer, the probability is R minus 1 over R plus B minus 1. And we know that these two probabilities multiplied by each other are equal to 1/2. Part A asks us how small can the number of socks in the drawer be. So obviously we know we can't have 1 sock in the drawer because we need to pull out at least 2. So I'm gonna cross that off. We also know that we can't have 2 socks in the drawer because if we pulled out 2 red socks and we only had 2 socks in the drawer, then our probability would actually be 100%. So it can't be 2. Let's start with 3 socks. Okay, in the case that there are 3 socks in this drawer, we know there have to be at least 2 red socks because we're pulling out 2 red socks. So the probability on the first draw is going to be 2/3, and then we multiply that by the probability on our next draw, which is going to be 1/2. And we want that to equal 1/2, and we can already see that this does not equal 1/2. The only thing times 1/2 that equals 1/2 is 1, so we know that it can't be 3 socks. So let's try 4 socks. We know we need at least 2 red socks in the drawer, so there are 2 cases, 2 red socks and 3 red socks. We know that it can't be 4 red socks because, again, like we said, if it was 4 red socks, then the probability would just be 1 that we pulled a red sock. The case for 2 red socks, on our first draw, we're gonna get 2/4. We know this cannot equal 1/2 because, like we said before, the only thing times 1/2 that can equal 1/2 is 1. So let's try the case for 3 red socks. So we know on our first draw, we have a 3/4 probability of getting a red sock. And in our second draw, we have a 2/3 probability of getting a red sock. This actually does equal 1/2. So we know the answer to our question for part A is 4 socks. And that's in the case where there are 3 red socks and 1 black sock. Okay, now for part B, which is definitely a little bit more challenging. We could do plug and play, which is what we just did. We want to see if we can find our answer a little bit quicker. So what I'm actually going to use is somewhat of a property. We know that our first draw probability times our second draw probability is going to be equal 1/2. And this is the formula we've made to represent that. We also know that the probability on our first draw is going to be higher than the probability on our second draw. Okay, say we have 2 numbers. And we know their product is AB. And we know that A is greater than B. And we can assume that they're both greater than 0. This inequality is going to be useful for this problem. So we kind of want to turn this like 2 variable problem into a 1 variable problem. Since the equation links R to B, I want to fix 1 variable like B and then solve for the possible values of R. So then we would know how small the total number of socks in the drawer contains. So essentially we're going to turn this into a bounded equation, and then we're going to test the candidates instead of, just doing the plug and play like we were doing before. Like we said before, up here, this is going to be a little bit important. We're going to use that here. And then I'm just gonna take the root of everything. Okay, and then I'm gonna solve for R. So let's focus on our upper bound here. And we're just gonna use some algebra to solve for R. So from here, we just isolate R by dividing this. And we're gonna get something like this. So I'm gonna bring this up to the top. And likewise, we can do the same for our lower bound. So we're given the following inequality. This part, you probably will need a calculator. We'll start plugging in b values and then seeing which eligible r values we get. And then we're gonna test if our equality holds. Okay, so we wanna test even b values. So for b is 2, 4.8, 5.8. So that means our eligible r would be 5, because that's the only integer in between those. We're testing if our first draw, which would be 5 over 7, multiplied by our second draw, which would be 4 over 6, does that equal 1/2? The answer would be no, so we move on to our next b. So it is still a bit of plug and play, but we're not plugging every single possibility. We kind of fixed our r and we've limited the amount of computations we have to do. I actually noticed a little mistake in my algebra. I'm just gonna fix this mistake. Okay, so let's test our next b value. If you use your calculator, 10.7 and 9.7. So that means our only integer value between those two is 10. And then we can check if it holds. So 10 over 14 multiplied by 9 over 13. Does that equal 1/2? No. Let's check 6. We're going to get 14.5. 15.5. And our eligible r is going to be 15. Let's check. So we're going to get 15 over 21. That's 14, 20. Does this equal 1/2? Yes, it does. What this tells us is that b is 6, r is 15. So the total number would be 21. Part B for me at first was a bit tricky. I did plug and play and I did get the correct answer, but then I was given a little hint that I should use this, this property, and then I checked my answer online, and this is the exact way the book solves it. I also think plugging in these values may take a little bit of time. If you wanted to expedite that process, you could actually write a Python script, which I will show. First thing we would do is import the math library. What I want to do is I want to define a helper function called the probability of 2 red, and it's going to take in our r and b. And what this function is going to do is just going to return what the probability is when we draw 2 red socks. And then we want to check if it holds. So this function essentially just checks if our function above, the probability of 2 red, if it equals 1/2. With Python, you kind of want to be careful with floating points, so you want to compare them directly. So I'm just going to compare it within a really small tolerance. Essentially, if the probability of 2 red is 1/2, it will hold. So essentially what this does is compares if the difference between the probability of 2 red and 1/2 is less than this really small number, which it just means it's equal to it. Then we're going to loop through the even b values. Let's just say it stops at 200, and it's going to skip every. We're going to put our lower bound and then our upper bound. I guess we didn't really need the lower bound because we can just initialize r to be the floor of our upper bound. R is going to be the floor of our upper bound, and then we just check if it holds for r and b. We should print. And we want it to break so it doesn't go through the whole loop once it finds it. Yeah, so when we run it, a little parentheses problem here. Now, if we run it, yes, it tells us down here our R, our B, and the total number of socks. So yeah, thank you.